Okay. Okay, that was not being recorded, so I'll start again from the top. So here I've been asked to give an overview of one of the important LiDAR retrieval algorithms and data products, because I think most people here are LiDAR people and will be interested in getting to know more about the data products, in some cases in which they've been asked to help evaluate or validate. And before I start, I'll just get this out of the way. I'll just remind people that all of the algorithms are detailed in a special AMT issue. If you Google AMT Earth Care Special Issue, this comes up. And I can bring the cursor down. Yes. Yeah, oh, this works. You have the introduction to the special issue there, and I can't remember how many papers there are, but quite a number of them, including high-level overviews, the extensive, let's say, really decades-long process of preparing for Earth Care by relying heavily on the CloudSat Calypso heritage and the development of novel test data sets. And then for every processor, you have things broken down per instrument. You have all the CPR algorithms, for example, the ATLID algorithms, and this in particular, I'll be talking about in a couple of minutes. And for more details, I'll just refer people to here.
Donovan and Talpi.
Yes. As well as, yeah, the multispectral imager, and then the multiple instrument algorithms in the radiative closure part. So all this is very, very well documented, and it was quite an effort to get all these papers together. It was certainly a case of thinking, oh, okay, it won't be too hard, but then when you look back and what you did throughout the years and what you had to finally document rigorously, then it was a big job. But anyway, it's all out there, and there's already plans for a post-launch special issue, in which the first exciting results should be coming out in the next months, hopefully. So if I can switch to, yeah. So now I'll talk about the ATLID profile processor, and that processor actually delivers four products. The ATLID Aerosol product, which is more or less, okay, first I'll set the context a little bit. As you know, if you've dealt with LiDAR measurements of clouds before, and aerosols and clouds are on fundamentally different scales. Aerosols, it's, in a lot of circumstances, okay to average the data for quite a bit. To improve the signal-to-noise ratio and not blur things out too much. For clouds, that's not the case. If you, let's say, would average, let's say, stratocumulus cloud retrieval, cumulus cloud retrieval, backscattered LiDAR signals for more than 10 minutes or whatnot, you're fundamentally not capturing the processes anymore because you're blurring everything together. So a lot of the processing has to do with trying to improve the signal-to-noise ratio of the data, which is never what you'd want, because it's a space-based system, and the signal-to-noise ratio will always be a challenge to overcome. So you do have to bin the data appropriately. So there's a lot of that is done. The decision about where the data can and cannot be averaged, a lot of that is done in the A-AER pass. And that stands for it originally stands for aerosol only, but it's really aerosols and, let's say, thin clouds. And then that's used to set the stage for a more comprehensive, higher resolution retrieval. The methods in A-AER, the methods employed to get the aerosol extinction and backscatters are, let's say, semi-traditional. So sort of a direct inversion based on the LiDAR equations. In the next step, which is done at a much higher resolution, which captures both the clouds and aerosols, it's an optimal estimation forward modeling approach. And for that kind of approach, you need to stabilize things. So it needs a priori information, and it gets that for at least the weak features from the first pass, which is A-ER. ATC is the athlete target classification. That's where it uses the retrieved extinction to backscatter ratios and the depolarization ratios, as well as auxiliary data such as the temperature and even geographic location and thresholds on the extinction itself to say what is cloud, what is supercooled cloud, what is ice, and what different types of aerosols are. And then there's another algorithm which we had to develop, but is really, let's say, the simplest of all of them is the A-ICE product. It's just taking the temperature, the extinction where we've identified the extinction of pixels identified as being ice clouds, and uses parameterization to predict how much ice water content is there. It seems a lot of people wanted it, but it's really almost not an algorithm itself. If you're familiar with bands, sometimes they have to produce these songs because they've signed a contract. There's a contractual obligation, songs or albums. This is our contractual obligation algorithm. So. But, there we go. So this is an overview of what I'd like to cover, and this is a quick overview of the processor itself, and then I'll spend some time talking about the product, so you'll have some guidance as to what to look for and when you want to for your own purposes. Yeah. Okay. There. Very good. So I'll cover that, and I just think I covered in the last word what the gross differences between these different products are, all produced by the same processor. And I'll show some examples. Talk about the quality flags, because that's important. Anyone that's worked with AOLS data, for example, knows that you keep yourself in a lot of trouble and get some weird results if you just go and average the data without looking at the quality flags. Always look at the quality flags. And then zoom in on a few more points of attention, specific points. So the processor, the athlete profile processor, it's not actually the first algorithm that's applied to the athlete data. The first is, and I won't cover this much in detail unless there's some need for it. The first algorithm to be applied is actually AFM, that's the athlete feature mask. And that uses a combination of a couple of techniques borrowed from image processing to identify areas where there are targets and what we can consider as clear sky. And that helps then my processor smooth and bin the data. So the first pass is this A-ER products, which produces, let's say, the optical properties, i.e. the extinction, backscatter, and depolarization ratio with a relatively low horizontal resolution, and it only works when features are considered weak enough. So in practice, that's most aerosol fields and thin cirrus. And then to go to higher resolution, then it uses the more advanced, which is being cut off here, optimal estimation-based procedure. So, and again, the joint, and just mention here that the Output products, all of, well, I won't say all, but just about all of the Earth Care products are reported on what we call the joint standard grid. So one of the big things about Earth Care that we really try to push is the complementary nature of the data and the synergetic use of the data. So all the instruments, of course, have different resolutions. But what we've done is, even at a low level, is the output of the algorithms should produce everything on a common grid. So the end user does not have to worry, ideally, about geolocating the LiDAR, the MSI, and the radar. That should all be done. It won't be done at level 1, you can't do that, but all the level 2 products, you should be able to plot on the same lat long and pixels and all be nicely geolocated for you. Of course, that's the ambition. In practice, it's proved annoyingly hard to get right, but we'll get it right. It seems that even between, and that's something fundamental, but not even the major space agencies are consistent when it comes to applying leap seconds, for example. Leap seconds.
Leap, you mean the leap year? The leap
No,
year.
there are leap seconds.
We don't know what is the leap.
A leap second is every so often in the UTC, there is a leap second added. You might not notice it,
leap second.
but and since 2000, there's been 3 of them added, and 3 seconds may not seem much, but when you're traveling at 7 kilometers per second, it's 21 kilometers per second.
Oh.
Why is that?
Why is that? Because the Earth's rotation is not not as constant as one would look. So so the length of the day does change, in the order of a second now and then.
Nice. But then when this was discussed, then did you have decided on a
Yeah, but this was 21 years ago, and then they've there's more of these standards out there than you would think. But yes, you have to, and when you want to get things right, you have to very much people have to be coordinated into what their time means, because there are different standards out there when you get down to the.
So how do you handle this leap second?
Well, every so often there's an international agreement that at midnight at such and such a date, there's a leap second, like a leap year. Oh, in Earth Care, yes. So we were for a while, Eason and Jackson were using, and different subcontractors, something with the subcontractors are not keeping their let's say their orbit libraries up to date. So in a way, you can think of this as software versioning, but with the universal time standard, and of course, in many applications, you have to, of course, you need to be using the right timestamps, otherwise.
This is a fine
There's
tuning.
lots of, and there's about 1,000 of these little details that I don't have to handle, but sitting at the table and people are discussing things. There's in the space business or aeronautics or anything to do with GPS, they spend a lot of time reading about time synchronization.
So do you have in the algorithm that you can pro in the section about how this correction is being
Oh, we don't have to worry about that. So that's it.
data that you receive?
Yeah. But it was between there's about the whole algorithm development process, and at the level 1 involves a number of subcontractors and streams, and then it's.
But for now, from the time that the satellite has launched until now, there is no leap second. So
No, but not everyone was coordinated in their time.
Yeah. And at some point in the mission, it will be some leap seconds there.
Yes.
Then we don't have 59 seconds, we have 60 seconds before the new minute.
Or something, yes, but that should not have to worry about that.
But also in the altitude, it's not so precise with the JV, the ellipsoid. Sure.
Well, it is precise, but that's another area, yes. And there's different standards as to what you consider to be
Above
with
sea level.
regards to the yes. And this created
the need for conversion above sea level from ESA side.
Yes. And this was one area where they responded to the needs of the Cal Val community, where people wanted to know that embedded in the products.
Yeah, because some
For us, it was a real pain because that meant we had to update, add one more line and about 40 documents. But
yeah, because for the people external, because they have used Calypso that everything is above sea level,
yeah,
it makes sense to have a continuity.
yes. I would agree, but yeah, I think everyone at this table would appreciate that sometimes it's a miracle that anything works at all because there's so many points in a chain where things can be inconsistent. So we had, yeah, so let's continue. So back to April. So, okay. So the first algorithm, AFM, which I'll mention, but I can't remember if I go in detail. But anyway, that tells you where the big features are, not what they are. A-AER uses that information to get sort of the smoother background aerosol and cloud fields. And then A-EBD uses the input from the AFM and AER to then go back and try to get the clouds and aerosols together.
So A-AER has all of this, and
This last one here should be A-EBD, but it's cut off.
it's the same product in the second and third box.
This is really not a product, but more a process.
Okay. Now, so they don't have unsmooth and smooth, they just have the smooth version. The retrievals in
yeah.
smooth version.
Now, in this A-EBD, though, we actually report in products to the end users at 3 resolutions. The highest resolution at 1 kilometer vertically or horizontally, and then smooth to what we call the medium and low resolution fields. And those are adjustable parameters, but medium resolution is on the order of 50 kilometers, and low resolution is in the order of 150.
This is
So
the feature.
on different circumstances, depending on the scene you're interested in, it may be more appropriate to use the high resolution or the low resolution or the medium one. For, let's say, homogeneous, for well-behaved aerosol fields, I would mostly always go to the low resolution stuff. But if there's clouds around, then the high resolution stuff might be more appropriate.
And maybe something that low high resolution is in terms of time, right? Not vertical.
No, vertically, it's always 100 meters. It's always the native resolution of the LiDAR.
In the future versions, when you update it during the mission, is it something that this could be changed instead of 115 and 120?
It can be, yes. We can.
If we see something depending on
If this 150 kilometers turns out to be, let's say, not suitable, it's over smoothing, then that could be changed.
How strong a feature is defined based on the SNR?
Yes, with some additions on top of that. Basically, we try to structure it where we still consider it valid to smooth the data and then do a LiDAR inversion on it. Of course, the LiDAR equation is very non-linear. So in a situation, of course, let's say where you have a strong cloud and then nothing, you'll get a very different retrieval if you average these signals over that and then do a retrieval, or if you do a high resolution retrieval and then average the data. So it's not perfect, but that's the philosophy. And when we do the smoothing to produce the medium and low resolution fields, the smoothing is segregated. So if things that are identified at a high resolution with clouds, we don't smooth over that. So it's only sort of so you get the idea if you have a weak scattering background, let's say mostly the aerosols, but the clouds are always sort of done at the highest resolution that we have, which at this stage in processing is 1 kilometer horizontal.
And this is also for the layers that may be found.
Yes. Yeah.
High resolution.
Yeah. Because in a lot of circumstances, it doesn't make sense to Yeah, we want the output of the outputs to reflect the real structure of the atmosphere.
So it goes through the future mask at 1 kilometer resolution, and then based on there, only if it is aerosol, it goes to high resolutions. If it is clouds, it stays to 1
Or low
kilometer,
resolution.
to low resolution.
Yes.
If it is cloud, it stays to 1 kilometer.
So the output fields are kind of a bit of a hybrid. So let's say the low resolution extinction product at the end of the chain is the fields, the aerosol fields that have been smoothed to 150 kilometers, but the clouds haven't been smoothed, but they're reimposed on top. So it's a little bit
It's similar with Calypso. Actually,
it's a bit, but it's
I mean, in the extent that they also superimpose different resolutions.
really much, yes. But this will be important, especially for people that want to assimilate the cloud and aerosol observations together, because it'll be in the same data product, that 1 pixel, they'll have to be able to track back to see what horizontal scale that's really represented. So in that I know from people that do a data simulation, they don't like that kind of thing, but we couldn't come up with a better solution. So yet another diagram. Things are the processor has different components and actually different algorithms built into it. So at the input, we have the level 1B, the XTSV, which tells us how to bin things to the joint standard grid. The XMET, that's our auxiliary meteorological data. So that comes from the ECMWF forecast model, and that's a product that follows the Earth care orbit. So that's where all our meteorological information comes from, as well as auxiliary information such as the ECMWF cloud forecasts. The cloud coverage is in there too, as well as surface information.
But from there, you get just the water vapor and the temperature for the retrievals from your retrievals.
Yes, yeah. But it does open the door to future developments in which people want to do online comparisons with, say, our detected clouds and with the ECMWF detected clouds are, or like an AOLIS, they found it useful for the clouds aerosol screening to use the model cloud coverage as part of the retrieval process. So we're not doing that, but for people that want to do something, their own thing with Earth care data, it opens up that possibility.
And in the future, in the beginning, you get the forecasts when they're first created. But then, is there plans for a reprocess with the meteorological data after the assimilation of the general satellites?
Thought about it, and probably, if things operate as expectedly, probably not.
Okay.
Because we don't see the real gain in it.
Okay.
But that remains to be seen. If someone can demonstrate otherwise, then so reprocessing efforts are costly.
I mean, because in the end, you will have the processes.
We will have reprocessing, yes.
Yeah.
So, but
In
the
the
reprocessing may not be, let's say, triggered by that. But if we go back, then of course we would use the forecast fields, but would use reanalysis fields, which would be better. And of course, there's the feature mask, and that is all goes to April. At first, there's the A-AER step, and then on to the E-EBD step. But the A-ICE algorithm and the target classification are both they're physically realized as subroutines, and both these they're independent programs, but they end up following the same loads. And at the end, we have the A-AER product file. This is probably going to be the most useful for people, as well as the target classification.
Is this level 2?
And these are all level 2 products. Level 2A, because they're single instrument. So, and again, just remind you, the target classification procedure uses a For the aerosols, it's mainly the correlation between the scattering ratio and depolarization ratio that we use to determine the type. For the, let's say, as a component, of course, of the cloud phase determination, we use something that's very similar to what Calypso did. That again, if you use the integrated attenuated backscatter versus the depolarization ratio, and I'm showing here is a relationship from Calypso, as well as these symbols are dots. These symbols are what you get from LiDAR multiple scattering simulation from a Monte Carlo model. So if you only have single scattering, the depolarization ratio for anything spherical will be 0. But because clouds, you get multiple scattering in them, so even if the cloud droplets are spherical, you get a multiple scattering induced depolarization, which looks like this kind of relation. And this gray area is the say roughly covers what the Calypso sees. So we'll see something, and well, we know we see something similar, and this is used. And anything, when we do this correlation, anything outside of this sort of gray area is ice and not water. So this helps a lot in the, especially in some areas of the atmosphere, you don't really need it because you should not have liquid below minus 40 kilometers. And it's very rare to have ice clouds at 2 degrees Celsius, for example. But where this is really important, of course, as you mentioned this earlier, is supercooled layers, which you cannot distinguish just on the basis of temperature. So won't go, you can't even really read this, but this is a flow chart of the many steps in the A-ER algorithm, and there's a lot of bookkeeping done in this algorithm. So some physics, but a lot of it is the processing of the different layers and try to determine what's what. And you can go, points, just people really interested, someone really interested. Yeah, that's all described in this AMP paper. And so what I mean by bookkeeping, well, there's a lot that goes on here to determine not only how the data is structured horizontally, but where you can consider the layers, where it's okay to consider things grouped as layers. Because again, the signal to noise ratio is not what you'd like. And we know things like aerosols are continuous, often with height. And because the next step involves a big minimization. In all these optimal estimation problems, you have a big vector with all your control variables. And then you want to minimize a function based on all these. And every one of these variables is a new dimension. So anything you can do to reduce the dimensionality of the problem helps a lot in the computational burden. So if we can represent the vertical structure of an atmospheric profile by 4 layers, as opposed to, let's say, 200 independent altitudes, then it really speeds things up. So this algorithm attempts to set the stage for that. So here I'm showing some example signals from simulations. Of course, of that Halifax scene that I talked about earlier. You see the aerosols here, the clouds here, and you can see that indeed things, are structured spatially very differently. And then you have the Rayleigh channel here. So the first thing, there has to be some sort of the feature mask, which has ran the particulate attenuated backscatter through a couple of steps. One of them is called a hybrid mean filter. So it comes from something you'd find in Photoshop, for example, where you take the median of the data in different directions. And it's very good at picking out strong features, but without blurring things. So you can think of this as sort of the first way in which we detect the very strong features, i.e. the clouds and the edges. So the output of that is then used to determine, let's say, what the strong feature mask is. So everywhere outside of this, the white areas are where we deem that it's okay to smooth the signals within a certain amount and still not bias things bad. So and then the strong feature mask is combined with the signals to produce let's say initially smooth signals respecting the mask. Then there is a simple division of these two, of the me and the Rayleigh, the particulate and the molecular backscatter gives us the LiDAR scattering ratio, which is then used to produce another mask in which you're not, then you don't want to then smooth over over aerosol and cloud features. And then there's another round of smoothing. And then you finally get around to applying the extinction and backscatter retrievals. So you can sort of see how things get sort of distorted here, but that's okay because this only sort of sets the stage for the next high resolution retrieval. And you can't, there's more sophisticated approaches out there. Recall, this idea came up over 15 years ago. Now there's more sort of rigorous methods out there for doing this that have been tested on Calypso. But still, they even I know some of the people doing this. But one of the big problems they have now is that, for Earth care, we have to go through 1/8 of an orbit in 150 seconds. These more advanced methods that they're developing for Calypso, they take about 4 hours to do that. So they still have some time to go. And again, so that was sort of the looking at how you can vertically smooth and bend the data, no, horizontally, and then there's a vertical component in which we use a number of strategies. So I'm zooming in on a section of that scene before, where we use a combination of the feature mask levels to break things up vertically. Vertically. So the solid lines here are where the algorithms have decided where you can bend things vertically using a combination of the feature mask and the low resolution scattering ratio. And this can be tunable. You can either tell the algorithm to be very aggressive in making many layers or being less aggressive. And that's something that we will have to tune. And hopefully then it's something I'd really like to use ground-based data, for example, in comparison with some cases where we want to know if we're getting the right balance between the number of layers. Because if we use too many layers, then our signal to noise ratio goes up. Things will get too noisy. If we use too many layers, we will be underrepresenting things. So, and then all this information gets sent to the next step, which is in its character a very different approach. Like I said, the extinction and backscatter retrievals done in the first step are relatively conventional. So you can start from the LiDAR equations, and to get the extinction, you divide by the atmospheric density and take the logarithmic derivative. So nothing fancy. Things have been in practice, much like you do for Raman or LiDAR retrievals in the conventional sense. So this is something a bit more advanced. Anyone that's data simulation or a lot of satellite retrievals use optimal estimation approaches. There's a lot of that in Shockley processing, for example. And the idea here is you have a function, which I'm denoting as sigma, and it's not really a chi-squared thing, in which you want to minimize this function here, which is a mathematical representation of the distance between your observations, the small y's, and your forward model observation. So y is you're modeling what the LiDAR signals should look like based on your state variables, which in this case is the vector of the extinction at every altitude. So we allow the extinction to be, we don't layer the extinction. The extinction can vary at every range gate. But the associated extinction to backscatter ratio is in layers. Because that makes more sense. The extinction we know is not, you can rarely treat that as one layer because it's always going up and down. But the extinction to backscatter ratio of the aerosol is one type. It's, you know, sort of okay to say it's 50 and don't really worry about if it's changing from 51 to 62 at the same level.
So this will certainly have then another resolution, right? So
Yes. So there's in a lot of the Earth Care products, there's a big difference between the grid things are reported on and the real resolution of the data. And that will be an evolving process. We have, you know, we're reporting what the layer structure is. But yeah, for the connoisseur, it'll be something that we'll have to dig in, and this is something that's relatively new. So this is something where that will be developing. And if there's real feedback from the user community about what we should be reporting, we can take that on board. But it is something to watch out for. And you can see this back in the plots. When you look at the extinction, you see, okay, it's clearly at 100 meter resolution. But when you plot the retrieved extinction to backscatter ratios, you can see it's blockier.
But in the product, the LiDAR ratio has the same grid as the extinction.
Yes.
Okay.
Because it was seen to be too much of a burden to report that in a different structure and then have everyone have to reconstruct things. Because then they have to order multiple files and know how things were mapped onto each other. And there's also particle sizes in there, which are important under some circumstances because they do go into a multiple scattering model. So we do treat multiple scattering effects. And that is from space, you almost always have to do that because you're so far away from the targets that multiple scattering is usually important. And we expect multiple scattering to be even important in some aerosol fields. Usually from the ground, you don't have to worry about multiple scattering in aerosols. But for things like sea salt, in which you can get an effective radii over 500 microns, from space, that's enough that we expect that we should be treating multiple scattering effects.
and what's the range of radii that you consider?
Depends.
Typing.
Depends on the typing, yes, because the counterpart to the state vector is the a priori state vector. So we don't attach any a priori values to the extinctions, but the LiDAR ratios and these especially, they are for every aerosol type. We have a priori that's linked to the type, and for the ice clouds, we have a parameterization that's based on the temperature. Sort of old-fashioned ideas, but they seem to work well. We will see. But anyway, getting back to this, so getting back to the cost function. So the cost function, it mathematically expresses the difference between your forward model and your observations, but also from your state vector, the distance from your state vector from your a prioris. So that's important to stabilize things. But in these type of retrievals, it's always important to have good error estimates. Otherwise, you can get very smooth, nice looking retrievals, but then you realize you're getting nothing more than your a priori out. And I know of a couple of ESA projects in which that had happened. And during the Cal-Val stage, after a year, somebody finally determined that the ozone profiles coming out of your satellite were nothing more than the A priorities. But you can see how that can happen because some software engineer somewhere, there was this parameter that they said, oh, now, okay, if this parameter is too small, things look too noisy, and sometimes the code crashes. But if we multiply it by a factor of 10, well, the code's faster and everything's smoother and it agrees with the zonal climatology. Oh, it must be right. And then realizing that you just get the A priority out. Because in that case, then you've made these terms very small, the covariance is very small there, and you're basically ignoring your observations.
Every time, every retrieval that you want to make, how do you choose the a priori variables? I mean, from a pool of from the lookup table?
Pretty much so, yes. So the a prioris, at this stage, things,
How do you know that this layer that you're observing has not an accurate particle size, but a distribution or
it does have a distribution. So in effect, yes, things are, yeah, if you look in the configuration file of the processor, that's all encoded there. There is a lookup table. And for the aerosol types, that is because things have been typed by A-EBD in the first pass. So we know this layer is, we're calling this layer marine aerosol. So we have an a priori for marine aerosol. Well, okay. Two things, okay. If the retrieval, if it's a weak feature that we have retrieved, we know that. We both typed that, but we also have the estimate of the extinction to backscatter ratio that was retrieved from A-EBD,
Not from AFM, from A-AER.
Yeah, AFM doesn't do any retrievals, it just tells where the features are.
Yeah.
So that, so this was done. So, but the A-ER, if it's, let's say, out here in this aerosol area, then that's as well retrieved by A-ER. So we know that, and we use that information to help set the a priori here. If it's a feature that we know that it's, sometimes we can actually sort of classify things based on smoothness, but we're not able to do a quantitative retrieval, and then we appeal to the typing. And that happens a lot in the water, in the ice clouds, where it's, we know it's an ice cloud, but it's been too attenuated or we can't do the traditional LiDAR retrieval there because it's too optically thick. So then we appeal to the typing. So sometimes it's a mix of both.
One dirty question.
Okay.
Oh, sorry. Honestly, there were some cases in my trial where I could get the a priori, at the end, like even this so that it was too equals to give me a solution. So is there any case where you really get a priori at the final product? For some retrievals?
Yes, there is for most of the, especially for the particle size. A-AER doesn't retrieve any particle sizes really. They're in there to help with the multiple scattering. So the information content in aerosols is really low there.
Okay.
And we do report things like the different components of the cost function. So at least you have some idea.
And what is the degree of freedom of something?
Oh, it depends on how many altitudes are.
Okay, yeah, because you do it at every.
But I mean, it's, yeah, for every altitude in which there has been a feature identified, that's one state variable. For every layer, that's another two variables.
Can the end user see the a priori?
Yes,
Okay, so it's in the product.
it's in the project. At least it should be there. If not, then it'll be there next
So
revision.
the end user.
But yeah, yes. But a lot of people won't.
I get but you will have a QA value associated with this quite
Yes.
flag, so
Yeah.
there's.
So we flag things like when there's non-convergence, when we think that the cost function has not been sufficiently minimized. So I'll talk a bit more about that, and that's something that we should be updating soon. See, like in every project, the documentation is always a little bit behind.
You have like described everything in the A-EBD or
Yes.
what is that?
Yeah. Well, I know actually we have something called in ESA language in this project, we have PDDs, the product definition document.
Like, okay, the product user.
Yes. So that's the, so of course the real good user wants to have both the A-EBD and the PDD, but
Can you modify the cost function on your baseline, or that's hard coded into the set analysis?
oh, no, this is all, everything beyond level 0 is all done on the ground.
Okay, so
And even some aspects of level 0 can be,
okay, so that can be improved on baselines if you.
Yes, yeah.
Is that really?
yeah.
Okay.
So we're at the stage now, but I've been very busy with the level 1 data, and we're already moving on to the level 2, and we have some good comparisons, but I also know of parts where the typing fails spectacularly. As opposed, the aerosol, the cloud aerosol discrimination needs some improvement.
Comparisons with what?
Well, sometimes it's just looking at the data with your eye and saying, okay, a 4 kilometer thick water cloud. I don't think so. Something's gone wrong there. Because there's right now, as we speak, there's a lot of aerosol up there. There's a lot of biomass burning. There's been a lot of desert dust, and sometimes the scattering ratios and even the extinction are so high that it's crossing the threshold that we thought was safe for clouds only. So we have to put a bit more logic in there too.
So now you are retrieving the products from the actual data, but in your institution, it's not available. You're not doing this.
No, it's with real.
Real.
Yes, and and that data is still technically under embargo from because we're still in the commissioning phase, but pretty soon we'll get the level 2 stuff. But but it won't be rock solid. Of course, there's no point fine tuning the level 2 before the level 1 is, and yeah, we're a little bit behind on that.
And one question.
Sure.
This triggers so much because the comment I did here was really on aerosol cloud discrimination. Yeah, this is what the reason I came here, because with Tripoli we have these false alarms that it's cloud, but then it's like dust. Yeah, like with dust we have plenty of problems at the end because it's like overheating.
Yeah.
So I wanted to ask you, how do you handle it when there is like aerosol cloud discrimination issue? Do you then flag it, or how do you handle this operationally, or do you handle it or not? Because for instance, we don't.
It's very hard to associate an error with a classification sometimes. No, maybe we should, but we don't at this stage. We don't have a confidence flag yet in the classification. And we could, and that could be a candidate for an upgrade.
But is it there a systematic issue? Like, for instance, I tell you on a place like between the dust particles and some clouds, we have systematically cities. Yeah. For other species, it's tough. It's tough to say. But for dust, I have seen it with like some LiDAR data that the team gave me here and so on. So would you also say that you have the problems with that?
Some, but a bit different. We have the luxury of knowing a bit more about the vertical structure, of course.
Yeah.
So we can assign a temperature to that, so that so you won't have. Dust for us sometimes can look like a nice cloud because be polarizing and kind of similar values for the extinction and backscatter. But if it's below, if it's above 0 degrees Celsius, well, then it's unlikely to be.
Yes. Okay. So you take.
But the elevated dust can be a problem. We do have a couple of steps to try to eliminate that. One, it often has a somewhat different LiDAR ratio, so we can use that. to look at it. But if you ask me if it's going to be 100% all the time, no. There will be cases in which elevated depolarizing radar, depolarizing aerosols can be considered.
So probably, I'm thinking again for me, yeah, so it's a little bit shellfish to do it now, but probably then the water vapor could also help on the discrimination.
Yes, we're not using that now, but yeah, and I think the ECMWF forecasts are good enough for that because, yeah, you.
Thank you, you helped me a lot.
Yes.
Yeah.
Because, yeah, of course, I mean, if it's, if the, on the large scale, if the ECMWF is reporting that things are far from being saturated, especially high up in the atmosphere, when you see something, it's probably dust and not.
Exactly. Yes.
And last question again, talking about dust, it made me thinking about the war that's happening at
Yeah.
So the dust, yes, from the bombings, is that the dust that will
Oh, it's we already know. You know, if you pass over the Ukraine, you see smoke plumes. You see every satellite does that anyway. Then if you go to any satellite imager, it's pretty easy to see from eye. Even products like there's different fire detection products usually used for forest fire detection, and of course you see So a lot of this data out there is from Earth observation satellites that are publicly available and were built with no military applications in mind. I'm sure are being used by whoever can get the data. But there's no way to prevent that.
Okay, we have another short break for lunch now.
Oh, okay.
Reconvene half an hour.
Okay.
Is it okay if we have this?
Yeah, everyone. I don't want to keep people from their lunch, so we'll start here.
Okay. So for the remote participant, we have a break for 1 hour for lunch, and we will reconvene in 1 hour. Now, 2.5 in Greek time, 1.5 in Central European. Okay, let's go first.
Let's all respond.